Dear students, welcome to class of data structure. In today's lecture, we are going to study about heap sort. So heap is almost complete binary tree. We are talking about binary heap here. We all know almost complete binary tree, that it is just like complete binary tree, but there is an exception that it may not contain maximum possible node at the last level, but last level must be filled from left to a particular point. For example, this is almost complete binary tree. This is also almost complete binary tree. This is also almost complete binary tree. This is also almost complete binary tree, but this is not a almost complete binary tree because it need to be filled from left to a particular point. So no node between the leftmost node and to a particular point must be empty. A binary heap can be of two types. It can be a max heap where every node is greater than its child. So for example, say 100, 56, 78, 23, 19, then 65, 54. So this is example of max heap. Every node, if you can see, it is greater than its children. Parent is always greater than its child, or it can be a mini heap where parent is always smaller than child. So this is a mini heap. These properties we have already studied of binary tree. This is 2 into I, left child, assuming that our index start from 1. So 2 into I will get left child, 2i plus 1 will get right child, and parent of node will get a floor of I by 2. Coming to algorithm, so Max-Heapify is an algorithm which works on a particular index. It takes particular index as input from a list of element, and then it checks whether subtree that is being built from that particular index is a max heap or not. If it is not a max heap, it converts it into max heap. So let's take an example here. A is the list of element, and from list of elements, suppose we are at this particular situation. Okay, and suppose writing the indexes, let I is equal to 2. So now this is I, this is L, this is R. We compare all these three here, since L is less than equal, sorry, AL is less than greater than AI, so AL is obviously greater than AI and largest, so largest will point here. Then we'll compare largest and the right child. So 8 and 3 are compared. Since 8 is greater, so largest will not change. And finally we'll check whether largest is equal to I or not. So largest is not equal to I, so what we'll do, we'll exchange I and largest. So finally what will happen after exchange, we'll get 14, 8, 1, 4, 3, 19, 7, 11, 1, 2, 3, 4, 5, 6, 7, 8. So this was our largest. Now finally Max-Heapify will be again called here. So now this will become I. Again we'll check, we'll compare with L. So this is largest. Now we'll compare the left child and right child. Since right child is not there, no comparison. Again we'll check whether this largest and I are same. So since they are not same, so they will exchange. Okay, so this is how Max-Heapify works. It takes an index as a input from a given list, and it checks whether this is max heap or not, starting from that particular index. Okay, so after Max-Heapify operation, we come to the build max heap algo. So build max heap means you are giving a list of element and you have to first create max heap before doing the heap sort. So build max heap works to create a max heap from a given set of elements, and finally we'll come to heap sort. So we'll understand each of these algorithms with the help of an example. Let's see. So this is the given question. We'll use build max heap. So first, the basic steps is that we'll create binary tree out of it. So it's 4, 1, 3, 2, 16, 9, 10, and 14. Now we'll apply build max heap algo here. The build max heap algo basically runs from n by 2 down to 2. Okay, so here n is equal to 8, so it will run from 4th index to 2, and at every index it will call Max-Heapify. Okay, so this is my I. So we'll compare and check whether it is a max heap or not. So we'll apply Max-Heapify. At I is equal to 4, so obviously it's not a max heap, so take it max heap, it will exchange what we'll get. Now again we are going to apply Max-Heapify on I is equal to 3. So 3 will be replaced with the largest of these three elements, I, 9 and 10. So after doing Max-Heapify we are getting okay. Then again sectorial until 1, from 4 to 1. Max-Heapify at I is equal to 2. So again you can see that 16 is greater, so it will be replaced here. Finally Max-Heapify again at I is equal to 1. So we'll compare this and this. So obviously 16 is the greatest. 16 will become parent, 4 will be shifted here, 10, 9, 3, 14, 1, 2. Again using Max-Heapify algorithm, 16, 14, 4, 2, 1, 10, 9 and 3. So now this became a max heap. So we have processed the build max heap algo along with Max-Heapify algorithm, and this list of number is converted to max heap now. So this is our max heap. Now second step is to heap sort it. So let's see how to heap sort it. So the max heap we got was so for heap sort what we have to do, we have to replace root repeatedly with last element. Fine. And apply Max-Heapify every time to make sure that after replacement it is still a max heap. So the loop run reverse. The heap sort calls a loop. Under it calls Max-Heapify. The loop run reverse from n to 2. Fine. So let's have here our step 1. So we'll replace the root with the last child and we'll disconnect the root from the heap. So last element is 2 because index is 8, that is last index. 14, 10, 9, 3, 4, 1, and this is 16. So see carefully, this 16 is not connected to tree anymore because we have cut it from the tree. So at every step we have to do the same thing. And now we'll apply Max-Heapify here. Okay, at I is equal to 1. Every time we have to apply Max-Heapify at I is equal to 1 since we are replacing the root. So after applying Max-Heapify, we'll get a max heap. Seven, 6, 5, 4, 2, 3, 1, and this was 16, 8. Again, step 2, replace and delete root. So replace and delete root with last element, obviously. So now last element is index 7 because index 8 is now no more part of the tree. So 3, 10, 9, 14, it's again cut from the tree. 4, 2, 1, and 16 was here. And again the same process, Max-Heapify at I is equal to 1. So after Max-Heapify, what we get? We get 10, 9, 3. Okay, here we have 4, 2, 1, and 16. Okay, so again step 3, replace and delete root with the last element. So now last element is at index 6. So again we got 3, 9, 10, 14, this is 7, this is 6, 4, 2, 1, and this is 16. Okay, and again we'll apply Max-Heapify. So MH at I is equal to 1. So we'll get 9, 3, 4, 2, 1, 10, 14, and 16 somewhere here. So 8, 7, this is 6, this is 5, this is 4, 2, 3, and 1. So 9, 4, 2, 1, 3, like this. Again, so the tree we got from our last step was 9, 3, 4, 2, 1, 16, 10, 14. Again, same thing, replace and delete root with last element. This was step 4. Last element here is 1. So 1 is here, 3, 4, 2, 9, 10, 14, 16. So 8, 7, 6, 5, 4, 2, 3, and 1. So again, we have to do Max-Heapify at I is equal to 1, and finally what we got? We got 4, 2, 1, 3. 5 is 9, 6 is 10, 7 is 14, and 8 is 16. Again, step 5, repeat and replace and delete root with the last element. So last element again is syntax 4, that is 1. So 1, 2, 3, finally 4, 5, we have 10, sorry 9, at 6 we have 10, at 7 we have 14, and at 8 we have 16. Again, Max-Heapify at I is equal to 1. So we are getting 3, 2, 1, 4, 9, this is 10, 14, 16. Again, replace and delete, that is our step 6. This was step 5, step 6. So 3 will be replaced with the last element 3. So 1, 2, 3 is at 3, 4 is at 4, 9, 10, 14, 16. Again, Max-Heapify at I is equal to 1. We got 2, 1, then 3, 4, 10, 14, 16. And so last step, so we were at this step, we got here 2 and 1 and 2, 3 was 3, 4 was 4, 5 was 9, 6 was 10, 7 was 14, and 16 was 8. So again we'll replace and delete. Fine. So 1 here, 2 here, 3, 4, 9, 10, 16, 18. Sorry, this is 14 and this is 16. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now all elements are disconnected, and these array indices represent the placement of element in the array. So what we got here, we have array. So at 8th we have 16, at 7 we have 14, at 6 we have 10, at 5 we have 9, at 4 we have 4, at 3 we have 3, 2 and 1, and finally it got sorted. So this is how heap sort works. Hope you have understood. So now let's go to the complexity analysis of the algorithms. So Max-Heapify basically take order of log n base 2 time y, because suppose we have a situation like this. Okay, so imagine this, and we are applying Max-Heapify here. So what will happen? First it will traverse from here to here, then it will traverse from here to here, and finally it will traverse from here to here. So at the end of Max-Heapify algorithm, how many comparisons basically we are making, and how many movements we are doing. So at every step we are doing 2 comparisons. We compare 1 with 14, then 14 with 9, 2 comparisons. Here again 1 with 8. So what will come here? 1 will go here, 14 will go here, then again we'll compare 1 and 8, and then 8 and 7. So again 2 comparisons. So what will happen here? Finally 8 will go here, 1 will go here, and finally we'll compare 1 with 2 and 2 with the right child, since right child is not here. So almost we are going at every step we are doing 2 comparisons, and this is the worst case scenario where the comparison has to traverse the whole depth of the tree. So basically at most 2 comparisons for depth of the tree. So complexity is order of log n base 2. This is the complexity of Max-Heapify. Now coming to build Max-Heap, let's understand. So if you see the algorithm of build Max-Heap, so here build Max-Heap algorithm is this. So from n by 2 to 1 it is calling Max-Heapify, so you may consider that complexity here is, consider that complexity of this build Max-Heap is basically n by 2 into log of n, because Max-Heapify complexity log of n, but this is not the case. So let's understand it. So suppose this is a heap. So there is a formula that at height h, max node is ceiling of, sorry, so max node is ceiling of n upon 2 to power h plus 1. Okay, at height h. So suppose this is height 0, this is height 1, this is height 2, this is height 3. So if we check it here, so total number of nodes here are 15 to ceiling of not h plus 1, it's basically 2 to power h. So 15 upon 2 to the power, it's h plus 1 basically, fine. So total number of node at height h, this is the formula. Total number of max number of node at height h can be n upon 2 to the power h plus 1. So 2 to the power 0 plus 1, that is equal to ceiling of 7.5, that is equal to 8. So 8 nodes are here. Similarly you can check for this height 1. So if h is equal to 1, then 15 upon 2, 1 plus 1, that is equal to 4. Fine. So if we apply in worst case Max-Heapify algorithm on each and every node, as in, although we do not need to apply Max-Heapify on the last level because it do not have any children, but suppose if we are going to apply Max-Heapify on each and every node, then what is the amount of work which is done? So total number of nodes we are having is n upon 2 to power h plus 1, and work done on every node, we have seen the complexity of Max-Heapify is order of h. So this can be, and since value of h will range from 0 to the height of the tree, and since it is a almost complete binary tree, its heights would be log n. This can be written as n by 2 we have taken as constant, we have here h upon 2 to power h. Fine. And this can be converted into n by 2 sigma h is equal to 0 to infinite h upon 2 to power h. This is a harmonic progression, and if you solve this harmonic progression, the value will get is 1 by 2. So therefore we can see that time complexity of build Max-Heap is order of n basically. Okay, so this is the time complexity of build Max-Heap. Now if we talk about time complexity of heap sort, it's very clear that this loop is running for n minus 1 time and Max-Heapify is called for log n time. So obviously time complexity of heap sort is order of n log n base 2. Hope this lecture was useful. Thanks for watching.